Welcome back. We're about to take a sidestep. You see, we've been dealing with equations like this entire time in all these videos prior to this. We're going to take a sidestep and no longer talk about equations, but we're going to talk about inequalities, specifically linear inequalities. And why this is the right time for this is because a lot of the techniques that you have used in solving linear equations, you can use to solve linear inequalities. So let's take a look at them. Firstly, everything on the board, you should be able to verify this at this point. Every single one of these, well, I can't say expressions, these math statements on the board right now are linear equalities, linear equations, if you will. They all have an equal sign. They all have a single variable raised to the first power. Even though we have two variables here, they're the same variable twice. So here's what inequalities do. Instead of having one side equal to another side, instead of having one variable equal to exactly one solution, remember that's what we normally get with linear equations, what an inequality does is it compares these two sides and it says one side is larger or greater than another side, maybe equal to it, or less than or maybe equal to it. That's what inequalities do. So in other words, what they're going to do is they're going to replace the equal sign in an equation with one of these symbols. The less than, the greater than or equal to, or the less than or equal to. So we're not going to be getting x plus 5 equals 2. We're going to be getting something like x plus 5 is less than 2. That's really interesting because what we're going to learn here, and I'm going to ruin the suspense for you, what we're going to learn is that there's a lot more than one number that works for that. For instance, negative 5. Negative 5 plus 5 is 0. That's less than 2. Negative 4. Negative 4 plus 5 is 1. That's less than 2. How about negative 3? Well, negative 3 plus 5 is exactly 2. Does that work here? We're going to talk about that. We're going to talk about what these symbols mean. Maybe we get this. Instead of 4 equals 5 plus 2y, 4 is greater than 5y. I said plus, but I meant minus. 5 minus 2y. Again, what we're doing here is not saying what single number works. What's the one value that works in this equation? Because we no longer have equations. We have inequalities. Saying there's a whole lot of numbers here that you can plug in that when you evaluate this side of this inequality, these numbers are going to be, well, 4 would be bigger than the numbers. 4 would be greater than all these numbers. Or, likewise, these numbers are less than 4. So we're going to find out how to reverse those inequalities as well. We can say the same thing at least two different ways. Now there's a couple other ones. So we've dealt with the less than, we have the greater than. We also have these two unique ones. Less than or equal to, and greater than or equal to. You see, what these do is these are not strict inequalities. Sure, we could have the right side as greater than the left side, or the left side as less than the right side. So this statement is said, 3x minus 1 is less than or equal to 7 plus 2x. So what happens is that if we plug in a number, we're going to say this is a true statement if the numbers make it so that the left side is less than the right side, or the left side equals the right side. So this takes the idea of an equation and just extends the idea. Sure, numbers that make this equal, they're solutions, that's great. But also numbers that make the left side less than the right side would also work. So let's recap before we go on any further. A less than inequality says this strict inequality. It says your left side must strictly be less than 2, like 1.9999999 forever, but not getting to 2. Okay, well, not forever, because that technically as a limit would equal 2, but something strictly less than 2. That's what that says. This says the 4 must be always bigger than, literally bigger than the right side, never equal to. As soon as we get inequalities that have this little line underneath it, that's a less than or equal to, and that's a greater than or equal to, saying that these ideas still hold true, but we also do accept the numbers that make the two sides equal. Like an equation does, just a lot more of them because we're letting this side less than this side represent more solutions. The last one, how about this? 9 is greater than, x is greater than or equal to 9. Again, we got a lot of numbers. Right now, you could probably think of a lot of numbers that's true for this inequality. Firstly, and I asked you a question over here whether or not negative 3 would work. Let's try that after doing this one. So if I plug in 10, 10's for sure more than 9, or 11, or 12, or anything larger than 9 would certainly work in that inequality, because anything larger than 9 is greater than 9. That's what this inequality represents. But also, because I have this equals, 9 itself is included. So 9 works. Because in this inequality, the greater than or equal to, we accept all the numbers that are more than 9, but we also accept 9 itself. That's different than over here. Over here, you can't accept the numbers that equal to. If I had done this right here, then yeah, sure. -3 would work. -3 would be part of the solution set, because we have +2 equals positive 2. That's fine. Or anything that makes this side less than 2. That's okay. As soon as I erase that, that's a no-go. So here's what we're learning about these inequalities. Number one, they're not exactly equations. They don't have just one answer. They have a whole lot of answers. In fact, they have an infinite number of answers. It's crazy. We're going to get this infinite number of answers called a solution set that's called an interval in just a little bit. We're learning they're not equations. We're also learning that there's a different type of inequality between those that can allow the equation and those that cannot. So these two inequalities, the less than or equal to and the greater than or equal to, they allow the two sides to be equal, and they also allow one side to be less than the other side or one side to be more than the other side. All the numbers that make these two sides equal, or that makes the left side less than the right side in this case, the left side greater than the right side in this case. Over here, basically the same idea, but we don't allow the numbers that make these two sides equal. So the inequalities work very similarly. Equations are okay here. Equations are not okay here. The numbers that make these two sides equal is what I'm talking about. Not okay, are okay. So let's talk about this a little bit more. Let's expound on how many answers we really get. Because over here, when we talk about this, there's a whole lot of numbers at work that make this inequality true. We're still talking about a true math statement here. We just have a lot more numbers that make it true. 9 works because 9 is equal to 9. That's fine because we have that. 10 works. 9.1 works. 9.0003 works. 37 works. 1,000,000 works. There's a lot of numbers that are in the solution set for that inequality. And that's exactly what we have. So we don't have just a single number anymore. These aren't just equations. Sometimes they allow the numbers that make the sides equal, sure, but a lot more than that. In fact, we get an infinite solution set all the time if we have a solution all the time with these inequalities. And we call this solution set an interval. So the interval is the idea that we're going to have a spread of numbers that are going to be solutions to these particular inequalities. So that solution set says all the numbers that work, that make the inequality a true statement. There's going to be an infinite number of numbers. We call that infinite number of numbers, that range of numbers, an interval. So we're going to spend a little bit of time talking about that. Right now I'm going to erase the board. I'm going to talk about just 4 inequalities. I'm going to show you how to write the interval on a number line, and then I'm going to introduce to you something called interval notation, which basically just abbreviates the number line. So let's take a look. At this point, all you really need to know is that these aren't equations. They have more than one solution. Here, the numbers that make the two sides equal are not okay. Here, the numbers that make the two sides equal are okay and are in the solutions. As I'm writing this on the board, what I'd like you to be doing is thinking of some numbers that make these inequalities true. Think about, more specifically, if I were to draw a number line, where those numbers are located in relationship to the number I've given you. So, for instance, in this case, does 4 make a true statement? Is 4 less than 3? Ask yourself this question in your head. So whenever you're asking or whenever you're trying to figure out what numbers are true for this inequality, we should be asking things like, in our head, is 4 less than 3? This is the less than inequality. Is 3 less than 3? Is 2 less than 3? Think about some of those numbers. I'm writing the rest of the examples, and think about where they are in relation to 3 on a number line. Are they to the right? Are they to the left? That's the question I want you to think about as we're writing the rest of these. Okay, here we go. So as you're looking at this example, we're going to try to plug in some numbers here. We're just going to try to guess and check our way through whether these make true inequalities or not. So let's try 4. Hey, is 4 less than 3? Well, obviously not, because you wouldn't trade someone $4 for $3. That doesn't make sense. 4 is greater than 3. 4 is more than 3. How about 3? Is 3 less than 3? And we mean strictly less than. The case where these two numbers are equal does not count as solutions for an inequality without the little equals sign underneath it. So 3 is not strictly less than 3 is how we'd say that. How about 2? Well, sure, 2 is less than 3, 1's less than 3, 0's less than. How about any negative number? Well, negative numbers are always less than positive numbers. So we'd have basically, well, could we draw it? Could we draw it on a number line? Number lines go forever in both directions, where we have positive to the right and we have negative to the left. So let's make an abbreviated number line. We don't need to make this to scale or anything. It really doesn't matter. What we need to know is where 3 is and where this inequality is represented on our number line. So you basically just answer the question for yourself if you were playing along. Are numbers over here to the right of 3, are those solutions? Are those less than 3? Do they satisfy that inequality? And the answer is no, we already answered it. The numbers that satisfy that inequality are numbers like 2, numbers like 1, 0, and all negatives. In other words, all the numbers that go that way. All the numbers that go to the left of 3 are numbers that are less than 3 on a number line. Now, one more thing I have to tell you. The number 3 is not included here, because we just explained this, we just learned about this, that with inequalities that do not have that line, the numbers that make both sides equal are excluded. They are not included in the solution set. So when you eliminate this, you eliminate the equals as part of the solution here. So 3 itself is not less than 3, therefore it can't be part of the solution set. Now that's really an interesting concept, because 2.999 would work, 2.99999 would work, 2.999999999, whatever, would work, but 3 itself doesn't. So we don't just stop, don't miss this, we don't just stop our solution set at 2, thinking, well, if 3 doesn't work, then 2 is the next number. That's not the idea. We can do decimals here. We can do lots of decimals here. So basically, every number up to 3, but not including 3, is part of the solution set. It has to be part of the interval. How we represent that, how we choose to represent that in mathematics, is with a parentheses. Sometimes, some textbooks, some teachers are going to use an open circle. That's fine also. The open circle just says you're not including that actual number. When we get to the graphing, we're going to be using that open circle to represent you're getting really, really close to that number, but you're not including that number in your solutions. I hope that makes sense to you. So think through the inequality one more time. Think about all the numbers that work here. Everything to the left of 3, everything below 3, negative sure, and up to 2.999, almost forever, would be included here. That would work. Those are less than 3. 3 itself is not less than 3. Because we don't have the equals, we do not include 3. It looks like we get all the way up to it, we do, but the parentheses means that we do not include that value itself as part of the solution set. Let's move on a little bit. If that doesn't make sense, watch that back, see if you can work your way through the idea of getting all the way up to a number but not including it. The next one, this x is greater than negative 2. Again, we can represent inequalities very well on number lines, at least the solutions of inequalities. Let's put the number that's given, this negative 2, on our number line. Now, I want you to think about what numbers satisfy this. What numbers work here? X is greater than negative 2. What numbers can you think of that are more than negative 2? Well, it wouldn't be negative 3, because what we know is that as we go left on a number line, we get smaller and smaller and smaller. What numbers are more than, greater than negative 2? Well, positive numbers would be, wouldn't they? If you have money, like $7, that's more than owing money, like negative $2. So we know that all the positive numbers are greater than negative 2. 0, having no money, is better than owing $2. That's greater than negative 2. Negative 1, owing $1 is better than owing $2. That's greater than negative 2. In other words, all the values, all the numbers this way, to the right of negative 2, would satisfy this inequality. How about negative 2.4? Well, no, because that's over here. That's going towards negative 3. How about negative 1.99999? Sure, that's going to the right. That's fine. Here's negative 1, so negative 1.999. That's in the range. If you plug in 1.999, negative 1.999, that's actually more than negative 2. I know working with negative numbers can get confusing, but the more we go to the right, which is why we use a number line to represent this, the greater the number we have. That's kind of interesting. Now, how about this question? What about negative 2 itself? Is negative 2 itself included in the solution set? 3 wasn't included here because we don't have the equal sign. Therefore, negative 2 itself is not included. Only the numbers larger than negative 2, to the right of negative 2, are included. Negative 1.99999 for a really long time, and greater than that. To represent this, we'd still use a parentheses, but we're going to open it towards the side of the interval. So we're opening it towards the positive numbers here. So what we're learning, and what I'm going to write down right below here, is that for numbers that are not included in the solution set, we're going to use parentheses. You know, one more thing. We can make it even easier. Because the only inequalities that don't include the numbers, the values, the given number, whatever you want to say, because the only inequalities that don't include that are less than and greater than without the little equal sign, then we can make this kind of rule. You're going to use parentheses whenever you see those two symbols. If you see less than or you see greater than, you will be using parentheses when you do interval notation. That's great. That saves us some time. I'm going to come back and show you how to do interval notation once we finish these other two. So let's look at x is less than or equal to negative 5. Well, there's a change already. Here's negative 5. I want you to think about the numbers that are less than negative 5, smaller than negative 5, less than, left than negative 5. Numbers like 10 are not less than negative 5. That'd be way more. So that's positive versus negative. Numbers like negative 2 are not less than negative 5. It's weird to think about, but if you owe someone $2, you have more than if you owe someone $5. Because once you get your money, you'd have more after paying off that debt. So if we have negative $2, that's to the right of negative 5 on the number line. Remember, 0 is over here. Negative 1, negative 2, negative 3, negative 4, negative 5. If you have to write the 0, that's fine. The numbers that are getting smaller, the numbers that are less than negative 5, the numbers that are less than any number are always to the left of the number on a number line. Just like the numbers that are greater than any number are always to the right of a number on the number line. That's going to give us a really cool way to kind of cheat at this in just a bit, and I'll give it to you. So the numbers that are less than negative 5 are numbers like negative 6, negative 7, negative 50, negative 1,000,000. All the numbers this way, to the left of that number. Now, immediately we know something different here. With less than 3, with greater than negative 2, we couldn't include those values because we can't allow the numbers that make the two sides equal to be part of our solution set. That's what strictly less than or strictly greater than means. However, what less than or equal to and what greater than or equal to allow is two cases. This allows all the numbers that are less than negative 5, these guys. But it also includes the one number that makes this equal. So these are the numbers that are less than negative 5, all these, or including the number that equals negative 5. Well, negative 5 itself equals negative 5. To show this, to show that we can include all of this stuff and negative 5, we use a bracket. Open it towards the interval, but we use a bracket. The bracket as opposed to parentheses. On graphing, you'd use a solid circle. So some of you might have to do that. It depends on what class you're in. But you might have to use a solid circle to represent this. So the big 10-second recap, the big note here, with inequalities, Less than and greater than do not include the actual number. You represent that with an open circle or with a parentheses. Less than or equal to, greater than equal to, you do include the number that's given. You include the -5 because it's saying you could be equal. That's totally fine. That's included in the solution set. We represent that with a solid circle, a closed circle, or a bracket. Now, the last one. Let's do this x is greater than or equal to 4. Let's think about the numbers. Think about the numbers that are more than 4. 5, 6, 7. That's pretty easy because we have a positive number here. All the numbers that are more than 4 are all the numbers that are to the right of 4. That works in general. So if you're looking for numbers that are bigger than a given number, they're always going to be to the right on a number line. So we're looking at numbers that go this way. Now, ask yourself this question. How about 4 itself? Is 4 itself included in this solution set, in this interval? Well, just look at your inequality. If you don't have this, the answer is no, and you use parentheses. It'd be like 4.000000001. That would work. Cool. 4.00000000001. That would work too. That's awesome. But not 4 itself. As soon as you do this, you say, hey, yeah, all those numbers to the right, but also including the 4, because we have these 2 cases now. The number's bigger than 4 and 4 itself. And we use a bracket opening towards the interval to show that. So let's make another note. You're going to be using parentheses for numbers that are not included in the solution set. You're going to be using brackets for numbers that are included for the solution set. And because the only inequalities that include those values are less than or equal to or greater than or equal to, we have ourselves a nice little rule. We're going to use some brackets for numbers that are included. That means whenever you see those 2 symbols, you're going to be using some brackets in your interval notation. That's the idea as far as how these inequalities work. There's only one more thing that I need to get going on, and to teach you how to abbreviate this. So what we should know at this point is that equations and inequalities are different. Inequalities have a lot more answers to them. They don't just have one answer. They have many, many solutions, an infinite number of solutions, an infinite solution set, or an interval. How we draw our intervals? Well, locate your number and locate where the numbers are less than, strictly, you use parentheses, not including the number. Greater than, without equal sign, parentheses, to the right. Less than or equal to, bracket because we're including the 5, and to the left. Greater than or equal to, bracket because we're including the 4, and to the right. Now, there's kind of a cool trick. This is a big if, so please don't skip it and don't misconstrue what I'm trying to tell you here. If you have your variable on the left-hand side of your inequality, do you see what I'm talking about? Do you see how the x here is on the left-hand side, the constant is on the right-hand side? So left-hand side, then less than. Left-hand side, then greater than. Left-hand side, then less or equal to. Left-hand side, then greater or equal to. If you have that, if you set this up this way all the time, not switcheroos where you have the number here and the variable over here, not that way, but if you have it where your variable's on the left-hand side, your inequality will always point to the direction that your interval is. So for instance, do you kind of see how that makes an arrow? Almost exactly like that arrow. It's kind of cool. This arrow points to the left. It says shade to the left. This arrow points to the right. It says shade to the right. This arrow points to the left. It says shade to the left, but include the number. This arrow points to the right. Look, it almost looks exactly the same as that. It's kind of neat. So this arrow points to the right. It says shade to the right. Include the number. That's how these inequalities work. So if you have them set up this way, less than is to the left, points that way. Greater than is to the right. And it points that way. If you always do that, set your variable on the left-hand side, you will point to the side that your interval needs to be shaded. Follow the rules for, hey, if you have strictly less than or strictly greater than, use parentheses. That does not include the value. Less than or equal to, greater than or equal to, that does include the value, use brackets, and you follow my rules, you almost can't get these wrong. They kind of draw themselves. So how do we shorten it? How do we abbreviate it? This is called writing in interval notation. So when we write in interval notation, it's really just a shortening of a number line. It's going to represent the same exact thing. In fact, we're going to use parentheses here, and we're going to use brackets here. So how we do it, I'm going to start with this one because I think you'll understand it better. Think about all the numbers that are more than -2. -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Do those numbers ever stop? It's a weird thought. They don't. You can't count high enough to not be more than -2. So you could count forever and you still wouldn't reach the end of the numbers that are more than -2. How you represent that in math is with the infinity symbol. So where this interval starts, how we do interval notation is you look at your shaded segment, you start where the interval starts from left to right. That's big for the next thing I'm going to show you, so don't ignore that. You start from the left of where your interval starts and keep on going until your interval stops. Here, our interval, so here's your interval notation. Our interval starts at -2, that's where our shading starts, and it doesn't end. It doesn't, or it ends at infinity is what we'd say. It doesn't really end. Just keep on going and going and going and going. Now, because we use parentheses here, because we have the greater than inequality, we do not have the equal sign, we're going to maintain that parentheses. And here's something special for you. Because you can't ever reach infinity, we always, no matter what, use parentheses for infinities. So look at this, it's kind of neat. This basically just shortens our number line. Instead of drawing a number line and drawing all the shading stuff and drawing where it's going, you just say, hey, my interval starts at -2 and it doesn't end. My interval starts at -2 and it doesn't end. This does not include the -2. This does not include the -2. This does not include the -2. They all say the same thing. All of them say the same thing. This is just interval notation. Now, let's try this one, because this one's weird. We always read from left to right in our graphing. We always do that with our graphing of inequalities. So when we're looking at this and asking, where does this interval start? It doesn't start at 3. In fact, it ends at 3. That's weird. It ends at 3. And it ends at 3, not including 3. So the question is, this is pointing this way, where does it start? Where does that actually start? If it's not at 3, where does it start? Really weird. It has a starting point at -infinity. As far left as you can go is where this inequality starts, from left to right. We always use parentheses for negative infinities, but you can go as far left as you want and you'll never run out of numbers. We just have to write this from left to right. So writing this is never appropriate because how interval notation works, it says you start at this value, you get bigger and bigger and bigger until you end with this value. You start at negative infinity, you get larger and larger and larger until you end at 3, not including 3. That's what this represents. All the numbers less than 3 are the numbers from negative infinity up to 3. This is backwards. This says you start at 3, you get larger and larger and larger and larger until you get negative infinity. That's impossible because numbers greater than 3 go that way. They never reach negative infinity. They just keep on getting positive infinity. So make sure this is in order. Make sure this goes from smallest to largest, even if you have to start at negative infinity. And you know what I would like you to do? I'd like you to try 2 more. I'd like you to try those 2 over here. See if you can write the interval notation underneath them. Keep in mind that now that we're including the value, it's going to look identical, except you're going to be using brackets for the numbers. So I'm going to give you a couple seconds to do that. Make a little side note here. Hopefully you'll do this as I'm crossing this out. Don't do this. So our interval notation for our last 2 inequalities. This inequality is really similar to our first one. This says our interval actually stops at -5. Does it include the -5? Is that included in the solution set? Yeah, you could be equal, for sure. Yeah, you got a bracket that's including that -5. So in our interval notation, we would stop at -5, and look how we're using the same symbols. It's kind of nice. This is just an abbreviated version of a number line. It's in the same order even. But to keep it in the same order, you have to start from the left of where this interval starts. So you have to start again at -infinity. This interval says, hey, the numbers less than -5 are way over there at -infinity. They go all the way up to -5. And because we can allow equation here, we include that -5. There's one thing that students do get tripped up on, so be careful here. It's really common for people to put a bracket because they say, oh yeah, use brackets. Brackets are reserved for finite numbers, not infinite numbers. So even though we use a bracket for -5, you can't actually get to -infinity, so we can't include it. That's why we use a parentheses for any infinity, whatever. The last one. This interval, all the numbers that are more than 4 start at 4 and they go to the right forever. All the numbers more than 4 are 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, all the way to infinity. So we're going to be ending this interval at positive infinity. Where this interval is starting, well, is at 4. Look carefully at the inequality. Hey, it says the two sides being equal is included here. The 4 itself is equal to 4. That's included in the solution set. That's included in our number line. That's got to be included in our interval. That's the idea. That's how inequalities play into number lines and graphing and in intervals. The interval should look just like your number line, only shortened. It should have a starting number. It should have a bracket just like you have a bracket, or a parentheses like you have a parentheses. It should read from left to right, smallest number to largest number. That's how they all have to work. You can't go from 3 to -infinity. It's got to be -infinity to 3. Other than that, keep in mind that, man, I swear, if you get your variable on the left-hand side all the time, these things point to where you're supposed to go. X on the left, go to the left. X on the left, go to the right. X on the left, go to the left. X on the right, or X on the left, go to the right. Just follow where your arrow is pointing if your variable is on the left-hand side. That's what I want you to know. We're going to do one more little example here. I want to show you just one last time on what solutions are. So if you've got this, you're probably fine. But let's check out one more just for thoroughness. A lot of times, many textbooks and a lot of teachers are going to put something like this on a test to see if you understand what solutions actually mean for inequalities. Let's do something like 3x minus 5 is less than or equal to 10. Now, we're going to get to solve these in another video. We're pretty close to it right now. But let's see if some of these values are solutions or not. Because I want you to really understand that there's not just one number that makes this true. There's lots and lots of numbers, an infinite number of numbers. You keep going all day long finding numbers here and you'd never exhaust them. How about x equals 2? If I plug in x equals 2, does this make a true statement? Plug it in. Use your calculator, use your head, whatever you want to do. Let's put 2 here. Hey, 3 times 2, well, that's 6. 6 minus 5 gives you 3 times 2 is 6. 6 minus 5 is 1. Is less than. Is that a true statement? If it is, then 2 is not your, get this right, please don't miss it. 2 is not your only solution, it's just part of the solution set. So 1 is less than 10, that's a true statement. So 2 is going to be part of your solution set, just one little number that works in this interval that we would be finding here. So yeah, 2 is a solution. How about 0? If I plug in 0, 3 times 0 is 0. 0 minus 5 is -5. Hey, is -5 less than 10? Every number in the world that's negative is less than every number in the world that's positive. So -5 for sure is less than positive 10. That's also a solution. Notice right now, these are no longer equations. We don't just have one answer, because if we did, this would be impossible. You can't have two actual solutions in an equation of numbers, okay, if you don't have infinite solutions for any number. So in inequalities, we're learning that not every number works, but lots and lots and lots and lots of numbers do work at the same time. Those are an infinite solution set, an interval. So we have two solutions here. How about x equals 6? If I plug in x equals 6, I have 3 times 6, that's 18. 18 minus 5, 13. Is 13 less than 10? And it's a ding, ding, ding. No, that's bad news. No, 13 is not less than 10. This is not a solution. So right now we're finding a number that's not in the solution set. Last one, and then we're going to be done with our video here. Let's plug in 5. If you plug in 5, you get 3 times 5. That's 15. 15 minus 5 is 10. Is that a solution? Well, that depends on the inequality. If you have the less than or equal to, or if you have the greater than or equal to, then this allows for that one number that makes the two sides equal to be part of your solution set. If not, then it says the one number that makes the two sides equal is not part of your solution set. So in this example, because we're allowing 10 to be less, 10's not less than 10, I get that, but this equal sign is allowing that equation part of it, that equal part of it, to play part of the team, okay, to be part of the solution. This would be a solution. Now think about this. What if I go back? Okay, less than, yes, less than, yes, less than, no, less than, no, but equal to, yes. That's what that equal sign says is okay to be part of the solution set. Now let's go back. What if I change that? If I change that, is this still a solution? Sure, yeah, it's less than 10. This, yeah, sure, it's less than 10. This, it's still not a solution. It's more than 10. This is no longer a solution. So that's the difference between inequalities that have the equals, less than or equal to, greater than or equal to, and inequalities that don't. Less than or greater than is whether or not we include the single number that would be found by solving an equation in the solution set. Here this would be no solution. That's really about it. Hopefully this has made sense to you, cleared up some of what inequalities are, and what you really need to get out of it is that if you set up your inequalities correctly with your variable on the left-hand side, your inequality will point to the direction of your graphing, of your shading on a number line. Use parentheses for less than or greater than, use brackets for less or equal to, greater than or equal to. I'll see you next time for solving these things.